I zoom in, it's just for, I mean, he'll be standing up, right?
Yeah.
So I think a little bigger is better. Yeah, something like that seems good. Okay. Is this on?
Testing.
All right, folks, I have a task for you. If you know anyone that could have shown up for this talk and didn't, afterwards go make them feel bad. It is my great pleasure to welcome Christopher Glein, this year's Midland lecturer. Chris gave an absolutely superb public lecture last night. How many of you saw it? Wasn't that awesome? For those that weren't there, the talk was about his findings of the elements necessary, or at least most of the elements necessary for life in the ocean on Saturn's moon Enceladus. This was a master class, I thought, in how to give a talk to a general audience that is at once accessible and deeply scientific. Again, I was very much blown away. It was recorded, and I encourage you to watch it if you're not able to attend. Today, he's giving a more technical talk, although I'm sure it will still be accessible, Bridging the Solar System Exoplanets Divide, Bridging the Solar System Exoplanets Divide, the Sub-Neptune Opportunity. Chris is at the Southwest Research Institute in San Antonio, Texas, where he works in the Division of Solar System Science and Exploration. He is perhaps the leading authority on the geochemistry of solar systems' icy ocean worlds, Enceladus, Europa, and Titan. He received his bachelor's degree in science from the University of Washington in 2006 in chemistry. He also was a minor in ESS, working with our own David Gatling and many others. His PhD is from Arizona State in 2012, and he held postdoc positions at the Carnegie Institution and the University of Toronto before joining Southwest Research in 2015. He's involved in significant international planetary science missions, including the James Webb Space Telescope team, the Europa Clipper team, and previously the Juno and Cassini missions to Jupiter and Enceladus. As we heard last night, he was instrumental, pun intended, in major discoveries on the Cassini mission in particular. His specialty is the development and application of methods that allow us to infer the chemical properties, internal processes, and evolutionary histories of these distant environments using spacecraft data. Last fall, he was awarded the Carl Sagan Lecture by the American Geophysical Union, a well-deserved honor that recognizes the scientist who embodies the late, great Carl Sagan's interest in astrobiology as well as effective science communication skills. See, that's why I didn't get the Sagan Lecture. Please join me in warmly welcoming Chris Glein.
Thanks, Eric. Thank you, everyone, for coming. Oh, and lights are even going dim. It's great to see so many familiar faces in the audience. I guess you're ready for round two, right? At first, before I want to kick things off, I got to thank Baptiste and Eric once again for inviting me to be this year's Mainland Lecture. It's really a great honor, and I've had a lot of fun, too. It's amazing what a lot of the faculty are doing here, and all the students, including many of you. I've met with 2 handfuls of graduate students over the past 2 days, and I've been absolutely amazed at the quality of their research and the questions they're trying to address. So, happy to be back. So today what I'm going to present is a new phase of my research program. It's a little bit different. So for many of you who came to my lecture last night, you might think of me as an Enceladus guy, or maybe an icy moons researcher, right? But that's not entirely true, at least not anymore. What I really strive to accomplish is to be a geochemist who's interested in a broad range of questions in planetary science and how planets work, and those workings can involve habitability and life, but they don't necessarily have to. So let's dive right in. So I'm going to start with what many of us are familiar with, the solar system. This is home, right? And for all of us who went through the school system here, we've learned that there are 3 broad classes of planets, right? So you have like the inner planets, which are known as the terrestrial planets. Some of them are kind of like Earth in the sense that they're all small and rocky. Then in the outer solar system, where we ventured last night, you have 2 classes. You have what are known as the gas giants, that's Jupiter and Saturn, and then the ice giants, Uranus and Neptune. And over the past several decades, we've developed models and frameworks to understand why the solar system is the way it is. So I've kind of given you a hint here where you could see that dashed line, right? That's labeled the snow line, and that's thought to be really important in defining where big planets versus little planets occur. Because once you're past the snow line, that means that water ice, or snow, can be stable, and that dramatically enhances the density of solids that are available to form planets. And that's why we think Jupiter and Saturn, Uranus and Neptune were able to grow much bigger than, Mercury, Earth, Venus, and Mars. So that was all great, right? But then something happened. It happened in the mid-90s. I was just actually a teenager at that time. So this occurrence was in my lifetime. There was a point before that time in my life and then after that time. And these 2 gentlemen, they're from Switzerland, caused this revolution to occur. So I'm speaking to is the exoplanet astronomy revolution. On the left-hand side, that's Didier Queloz, and he was a graduate student working on studying the way that an unseen planet could tug at its host star. And on the right-hand side is his advisor, Michel Mayor, and he helped to develop that approach. And they were the first to discover a planet orbiting another main sequence star like the sun. So this planet was called 51 Pegasi b, and it's a little bit bigger than the sun is. But this effectively opened the floodgate, and it shattered that perfect picture we had just looked at. And this is from a paper published last year where they compiled a lot of the statistics from the exoplanet archive. But if you look at all these data points, so what's plotted here is on the vertical axis star mass relative to the sun, and on the horizontal axis the distance that an exoplanet orbits from its host star. And you can see that there's a lot of data points, and they don't really follow any particularly clear trend. They're just kind of everywhere. I want to highlight two really important features of this distribution. One is you can see, let's see if you see the highlighter. Okay. Yeah, so here's Mercury, and then you can see there's a lot of planets that occur interior to the orbit of Mercury. So that's a really foreign thing to us because we thought Mercury is very close to the sun. And then the other major findings, if you look very carefully at the colors of these different findings, there's a lot of red colors close to their host star. And you can see in the small legend, I apologize, so we have the gas giants, we have the Neptune-like, we have the terrestrial, and then there's this fourth category, which is those red points. And those are, in this figure, those are labeled the super Earths. So that's a really important finding that came out of these massive surveys like the Kepler mission from early in the last decade. Here's just a zoomed-in perspective at these very intriguing objects. So it's plotted here as the average, from a statistical sense, the average number of planets as a function of planet size. And so this captures but resolves that super Earth category. You can see it's actually split into two different size classes. One is super Earth proper, which from studying both the size and the mass, you can get the density. You can find, okay, these things are big chunks of rocks, kind of like the terrestrial planets. But then there's this other distribution to the right-hand side that peaks around 2.4 Earth radii, and those have become known as sub-Neptunes. So they're in between the size of the Earth. So on this plot, Earth has a size of 1 for the Earth radii, and Neptune occurs around 4 Earth radii. So you can see the sub-Neptunes are right in that zone. And on the right-hand side, those are just various depictions of what their interior compositions might be. The bottom line is they are unknown and mysterious. And this just puts into words what I just said here. We've learned that planetary systems can be much more diverse than we once thought. That very neat classical vision of the solar system. And these sub-Neptunes, they appear to be the most common size of planet that nature produces. And we don't find them in the solar system, so we're kind of lost, which could be bad, or it might be an opportunity, right, to learn something new. And that's the way I approach this, is as an opportunity. And it's a really simple question that many of us might be thinking right now, which is listed right here. What are they like? And I know I kept hammering you guys with analogies last night, so I'm going to do it maybe one more time here. I like to view these sub-Neptunes as like, the unknown land, terra incognita, with a question mark there, because we just don't have a good sense of what they're like. And we've dealt with similar questions before, when planets were just part of astronomy. And the analog I'm going to introduce here is the planet Venus. And I had some great discussions about Venus with some of Josh's students today. That was really delightful. So Venus is the one planet interior from Earth, so it's closer to the sun, and you probably know it as the morning and evening star. It's very bright. And over a century ago, Venus was in this unknown land as well. It was known as an astronomical object, but we didn't really know what was it like. And so what happened at that point when it was only in the domain of the astronomers? Well, Venus was very bright, so people inferred, and they inferred correctly, that it must have clouds to reflect a lot of the light, so it had high albedo. And the chain of logic goes, well, if it has lots of clouds, they must be made of water, because we have water clouds on Earth. It also is found very much closer to the sun, so you have these water clouds, and it must be very warm there. Aha! So it must be a swamp. And if there's a swamp, well, there must be a bunch of ferns growing in the swamp. And if there's ferns, there must be dinosaurs on the surface of Venus. So that was actually the prevailing view at the turn of the 20th century, is that Venus could be this hothouse version of Earth, kind of like the Cretaceous period on Earth, where you could have had these very exotic creatures. But the point is, when it was squarely in the hands of astronomy, Venus, all these different possibilities were in play. And we know today, of course, after studying Venus from the space age onward, that Venus is much different. It's perhaps less romantic than we had hoped, right? Because Venus is named after the god of love and beauty. And so this isn't too beautiful to some of us when we know Venus today is a hothouse. It's like hell down there where it's over 700 Kelvin in surface temperature. But that's the way it is, and we need to know the way it is. So what's happening today in exoplanets, I believe, is very comparable to the early steps of when astronomy became planetary science. And this paradigm shift is being driven by technological advancements. So you probably have heard the James Webb Space Telescope was launched a few years ago, and we're finally getting the data to transition from that romantic vision of what these places might be to real models that are constrained by data. So it's super exciting. And when you imagine exoplanets moving, I wouldn't say it's being completely removed from the astronomers' hands. They're now sharing it with the rest of us. We're geologists, or we're geochemists, or geophysicists even, and they're now going to share these planets with us, and this field of exoplanet astronomy, I believe, is becoming exoplanetary science, where these exoplanets, instead of these astronomical objects, they're also worlds. I think many of us view them as worlds, not just points of light that you can map out, but actual bona fide places with complex histories and geology and diverse processes. So that's exciting. What's even more exciting for me is I talked about Carl Sagan yesterday. I was jealous of his generation, the greats of Sagan, Gerard Kuiper, Harold Urey. They were fortunate to be born at a time when that romantic vision of the solar system transitioned into a scientific discipline. They were the first generation and the only generation to see the solar system transformed. And then the rest of us have been looking deeper at it, but it hasn't fundamentally changed for the most part. But the beauty of our times now is we get to participate in that kind of transition, right? Where now the exoplanet astronomy is becoming exoplanetary science. And we're the first that get to lead this transition. I think sub-Neptunes are ground zero for this new field to take off because they're so unknown. It's like landing in the middle of a new land, and you can go in any direction. And another way I think about these planets that's really exciting is the James Webb Space Telescope is so incredible that each observation is like taking a new mission to a planet. So I told you all yesterday, if you're at my lecture, we spend decades working on missions to go to Enceladus or Titan, Europa. James Webb can look at a new planet. It's effectively like taking a mission to that planet where we get brand new information. And there's over 6,000 exoplanets out there. So that's incredible. And so my goal in this talk is to highlight some recent thinking and insights from these observations of exoplanets. And I'm going to focus on sub-Neptunes. So we're going to start with this sub-Neptune known as K2-18b, the infamous K2-18b if you've paid attention over the past year, because there's been a lot of debate back and forth in the science community about what's actually happening there. K2-18b, as I mentioned, is a sub-Neptune. It has a radius that's pretty comparable to the most frequently observed size of sub-Neptunes. This is just an artist's impression of the relative scales of the Earth and K2-18b. So it's kind of a big boy, right? It's a big planet. It was discovered, so the name is K2. It was discovered during the extended phase of the Kepler mission, so the K2 part. And it's the only known planet that orbits that star K2-18. The B, for those of you who don't know exoplanets, the star is A, so B is the first planet that's found. And it was discovered using this method known as a transit method. And the way that works is if the planetary system is properly aligned with the observer, so us here on Earth, if the planet passes in front of the star, it briefly dims the star's light that we see, and you can actually detect that with an extremely sensitive telescope like Kepler was designed to do. So that just shows, you saw that dip, that means there's a planet there. And K2-18b is special because it's actually one of the colder exoplanets. There's an inherent bias to transit observations where the ones that are very close, they have a short year, right? They're constantly going around their star quickly, so you can just naturally observe more transits. The ones that are far away are harder to see. And K2-18b is fairly far as far as exoplanets are concerned. You can see that it has a very long year of 33 days, 33 Earth days, which is long for an exoplanet. It orbits close to its star, though, so it's 0.16 AU, closer than Mercury orbits our sun. But what's special is that orbit around that star occurs in the conventional habitable zone where liquid water could exist on the surface. And the reason why it occurs in that zone is because its star is very faint. It's an M star, which are the dimmest stars along the main sequence. So it orbits close to a little ember of a host star. And people have calculated that if K2-18b has roughly like an Earth-like albedo, then you can just solve the simple energy balance and you can predict the equilibrium surface temperature would be kind of like Earth's. So the amount of stellar installation is very comparable to that Earth receives. But K2-18b is a strange beast. So this is a diagram showing just some basic properties, the density of a planet. That gives you a first-order understanding of its composition. So there's Earth, there's Uranus and Neptune. Earth's a rock, so it's dense. It's made of silicates and metals, right, in the Earth's core. And then Uranus and Neptune have a lot of ices and gases, so they have lower densities. K2-18b falls into this no person's land, right, where it's like in between, and we just don't really know what to make of it. So astronomers are pretty clever. They also know some geophysics. And so what they like to do is they like to make these diagrams known as a mass radius diagram. So you can plot different combinations of materials, pure materials or mixtures of them, and you can try to predict what the radius should be for different masses. And that's shown in this diagram here. And one of the interesting things about this diagram is you can see some of these curves, like let's say way down there, the red one, that'd be pure iron, right? And you can move up here to like an Earth-like composition. K2-18b has a bigger radius than you'd expect for those compositions. Interestingly, if you had a pure water planet, that would be kind of close. Or if you added a little bit of gas for an atmosphere, then you could reproduce K2-18b. So it was suggested that the mass radius constraint is consistent with a massive water world in the habitable zone. So this is kind of exciting. And then what was done is this new type of planet was hypothesized, and it was called a Haitian world. I find this is a very interesting model to consider. And the name, I guess, was clever, right? So what Haitian world means is it's a hydrogen atmosphere above a liquid water ocean. And the type of planet was actually co-opted. So the person who invented this name, the concept was originally invented earlier by Dave Stevenson at Caltech. He suggested that you could have hydrogen on top of liquid water, and Ray Pierre Humbert also investigated this type of planet, but they didn't call it Haitian world, but it's effectively the same thing. And these kinds of planets, if they exist, would be totally alien because you would have a huge water layer. And this would be really great for Professor Journeau because he likes studying high-pressure ices, and you can see like this whole planet is almost a high-pressure ice. But yet, if you're in that habitable zone, the surface environment could be melted, and you would predict from these simple types of models that you could have an ocean that's much deeper than Earth's ocean, and in fact, much deeper than any other ocean in the solar system, because, there's Enceladus, I mentioned last night, has a 40-kilometer deep ocean, we think, and this ocean could be anywhere from 50 to 350 kilometers in depth. This created a lot of excitement to imagine if this might be a new type of habitable environment. And when I heard the name Haitian world, I thought about it a little bit differently because I come from the world of geology. It reminds me of Lost City. So Lost City is a hydrothermal vent system at the bottom of the Atlantic Ocean. It's a really strange and wonderful environment where ultramafic rocks are reacting with seawater, and through the geochemistry of that interaction, the fluids are loaded with hydrogen gas, so H2. So you effectively have like warm water that is highly concentrated in hydrogen gas. And that's a habitable environment that we find on Earth. And this kind of reminds me of K2-18b, or at least this Haitian model of that type of planet where you could have liquid water in contact with a great deal of hydrogen gas. So with that backdrop in mind, there was a lot of interest to acquire data from K2-18b and other sub-Neptunes to try to understand their nature. And our key workhorse in that respect is the James Webb Space Telescope that was launched on Christmas of 2021. And it started science operations the following year, and it's been observing everything. So the galaxies, you've probably seen galaxies, exoplanets, it's been observing molecular clouds, protoplanetary disk, you name it, it's been observed, or it's planned to be observed. It's a flagship mission of NASA's Astrophysics Division, and it was a $1 billion mission, roughly. So big investment. And when James Webb looked at K2-18b in its first year, this is the transmission spectrum that was acquired. So what's a transmission spectrum? I mentioned we detected these types of planets when they transit the face of their star. It's like a mini eclipse. And some clever astronomers figured out that when that transit event happens, the atmosphere partially blocks the light from that star. And it actually creates a spectral fingerprint that you can derive. So if you know how to do this, you can actually create a transit spectrum. It's a little bit different from a classical absorption spectrum that you see in reflected light, where the peaks are actually inverted. So if many of you have seen albedo spectra, it'll be like a dip. In this case, if a molecule absorbs, it's actually a little peak that's produced instead. And what they found is that this atmosphere, it's hydrogen rich, so it's some kind of primordial atmosphere, but they also found other molecules like methane and CO2. And I won't talk about that other molecule because that's a can of worms. Right, exactly, algae. So then once those observations were made, the initial interpretation was guided by some of these first models that were developed, and the null hypothesis, if you will, is the mini Neptune idea. Because they're sub-Neptunes, so maybe they're just like scaled down versions of Neptune or Uranus. And so people constructed models of the atmospheric chemistry of a mini Neptune that receives this amount of starlight, and you can predict what abundances you might find. And CO2 generally is not predicted to be abundant in that kind of environment. With lots of hydrogen and high temperatures, it favors methane. But if you have a liquid water ocean at the surface, then models predicted you should find CO2, kind of like on the Earth. And another key indicator was ammonia. This was a big focus of the effort, was to search for ammonia, and they didn't find it. And they actually estimated a relatively stringent upper limit shown with this dashed line right there for ammonia. So it seemed like the simplest explanation could be this Haitian world model, where we know that ammonia is very soluble in liquid water. So that would provide a natural way to explain why you wouldn't see it. It's all dissolved in liquid. So it was proposed, based on the first JWST observations, that this looks kind of like a Haitian world, and this got a lot of people excited. I must admit, I didn't actually pay attention to K2-18b until these first data were published. I was sitting in a hotel room, and somebody just texted me and said, "You should go on the news and see this. Somebody's talking about an ocean world. What's this about?" And so then I went on the website. This is from a NASA press release, and I looked at this spectrum. I thought, wow, this is kind of cool. And this looks familiar again. This looks kind of like the plume that I've been studying for quite a while on Enceladus. It's not a perfect match, but there's some similarities where you have like hydrogen present and CO2 and methane. And it's proposed that you could have a liquid water ocean at the surface. So I thought, I wonder what we can do with that. What do you think we can do? Well, if you were at last night's lecture, maybe you would feel inspired to do something like this. So on Enceladus, we had to make measurements of these molecules, and from those measurements, we could then estimate one component of habitability, which is how much chemical energy might be available. So I thought, okay, well, what if we could do something similar? Because to make this kind of plot, you need measurements of CO2, hydrogen, and methane. And that's what was reported on K2-18b. And it was inferred that it could have a liquid water ocean. So I thought, well, why don't we try that? So here's the plot that was made in my hotel room, actually. The next night, I think, was the first version of this plot. It wasn't quite as nice as this. But in the line shown there, that's just one nominal case for 1% CO2 and 1% methane. If it was relatively clement surface conditions, so 25 degrees C. And what was interesting there is you could see that there's Enceladus' ocean that was estimated from Cassini data. And I claimed last night that there's a lot of energy that seems to be escaping from Enceladus. And this line is even further above Enceladus, and it's well above the minimum requirement to sustain methane-producing microbes. So that I also, the data have some uncertainties, right? So you can kind of play around with the error bars on the abundances of species. You can also play around with the temperature at the surface, because we don't know that. So you can generate these other predictions from the observations. But you can see for many cases, you could have habitable conditions with abundant energy to support life. So I thought this was kind of interesting as an exercise. And here's just a simplification. I mentioned last night that Enceladus is erupting 300 cheese pizzas an hour. This kind of environment, if it is in fact true, would be like a pepperoni pizza, right? So it was interesting food for thought. I'm not totally convinced, though, and I hope you're not totally convinced, because we got a long way to go, but we're starting to form some interesting thoughts about what might be happening. And so this is my final slide of K2-18b. I am currently feeling a sense of optimism and caution. If we find planets that are Haitian worlds, like suggested for this planet, what we now have is we have a geochemical framework that we can use to estimate supplies of chemical energy, and we could start making quantitative inferences about habitability. And I think that's a good step forward for the field. We're starting to merge that thinking from the solar system to the great beyond, right? But like all interesting things in nature that are complicated, there's other possibilities. And since the initial observation was reported, there's been a variety of studies suggesting alternative hypotheses to explain the data. I think that's great because it means that the field is moving forward and we're starting to ask more detailed questions and re-examining our data. So with that in mind, I'm going to explore another example that deal with the less optimistic version of how sub-Neptunes might be. And this is another cool paper. So I mentioned like the floodgates were opened for exoplanets, and it's really true. Like I was, I forget what I was doing. I must have just been wasting time somewhere. But I saw a paper come on Archive in, I think it was like March or April of 2024, after I just worked on K2-18b. And this was another observation of a different sub-Neptune called TOI 270d. And you might think it's amazing I can remember these names. It's actually really, really hard. You have to work on these planets for quite a while. This planet was discovered by a more recent mission than Kepler. This is called TESS, the Transiting Exoplanet Survey Satellite. And it was meant to follow up on Kepler. So Kepler had a very wide field view of a bunch of stars, but some of these stars were really far away. And we wouldn't really have a good opportunity to get spectroscopic data because they're so far away. But TESS was meant to look at a lot of closer stars where we could perform more detailed studies. And TOI 270d was one of the planets that was discovered, and it's fairly close from an astronomer's point of view anyways. So it's about 73 light years away from Earth. K2-18b, I forget the exact number, I think it's like 130 light years or something like that. It also orbits very close to its host M star, and it's another example of a temperate planet. So this is kind of a squishy term that the astronomers like, and that just means like it receives an amount of light from its host star that's roughly of the similar order that Earth receives. And it's like a new regime for studying exoplanets. And it again falls in that no person's land of bulk density where we're not sure what the hell's going on, so it makes it interesting. And the data that report on the Archive that I mentioned, these were collected as part of a larger observing program that was led by an astronomer named Bjorn Benneke, and these data were fabulous. They're even higher quality than the K2-18b data. So you could see, the worst thing I've learned that astronomers hate to see in their spectra is a flat line. Because that just means that they can't detect an atmosphere and you can't really say much about the planet. You could say potentially it has a high molecular weight atmosphere, but it's very difficult to dig deeper. And this planet has big features for a sub-Neptune, so you can derive the composition of the atmosphere using these instruments on JWST. So one's called NIRISS, and that focuses on the shorter wavelengths of infrared light, and then the other one is called NIRSpec, and the G395H grading is the high-resolution grading at the longest wavelengths, around 5 microns it cuts off. And they found a lot of those familiar molecules that we saw from K2-18b earlier. Sorry if this is not too visible. They found CO2, methane. We think it's a hydrogen-rich atmosphere. And as a geochemist, I got super excited because they reported quantitative information on composition. So we can now start doing geochemistry on a sub-Neptune. And in this case, I want to focus in on the CO2 to methane ratio that was derived in the atmosphere. Now I'm going to take you back into the dark past. Remember 2008? I was actually a grad student at ASU. This is when I first got into Enceladus, and the CO2 to methane ratio was observed in Enceladus's plume. So this is another example of how the solar system gives us clues of what to do. And at the time, this is actually my first PhD project, we were interested in constraining the temperature of Enceladus's interior using this ratio. So for many of you who are geochemists, what this basically boils down to is an application of geothermometry. You're using some kind of observable to infer deeper into a planetary body. And for Enceladus, we were able to then construct this kind of plot here where we could make some assumptions and then use that ratio to constrain what the temperature might be in the deeper interior. Well, I thought, wouldn't it be interesting if we could do something similar on an exoplanet? So here's the chemical reaction that's of interest, methane going to CO2, and you balance the reaction with water and hydrogen. This is a hydrogen-rich atmosphere. And I know you shouldn't show equations, but I want to show one equation. So this equation here, for all my geochemist friends, it relates equilibrium constant versus the fugacities, or you can simplify the fugacities in terms of partial pressures, which then reduce down to mole fractions. So if you do the math and work it out to the right-hand side there, what you end up having is equilibrium constant. It only depends on temperature, which is great if you're doing geothermometry. And on the right-hand side, you see the CO2 to methane ratio. And then you have some other quantities like the mole fractions of hydrogen and water. And then you have the total pressure. So when you take a junior year level class in geochemistry, what they tell you we like to do is we like to take the logarithm of everything. So if you do that and then you do some algebra, right, you can actually rearrange that equation, and then you can write the pressure as a function of log K, so that's where temperature enters, and then you have some of these other compositional variables, including the CO2 to methane ratio. So what I decided to do is, okay, let's try to solve this equation for the exoplanet, and you can define a limiting case. So I call this the high pressure case, and you can ask yourself, well, based on the observational data, what are the limits of those data that would allow me to draw a curve that maximizes the pressure? And so you can just look at that equation. Okay, so I want the water mole fraction to be as high as possible. That's consistent with the data. And then I want the CO2 to methane ratio to be as low as possible because there's a negative sign in front of the logarithmic term. So if you do that, you can then just draw this equation, as Bruce Nelson showed me long ago how to do these things. And then you can take some of the things that are harder to do, that the exoplanet astronomers are very good at doing, which is deriving radiative convective profiles of the atmospheric temperature as a function of pressure. And if you define then limiting cases like that, which I call cool atmosphere and warm atmosphere, then you can, like I did last night with Enceladus, you can find a sweet spot, right? Where's everything consistent? You need to be between the blue curve and the red curve, and then you need to be somewhere above the green curve. So there's where you are. And we define this as the apparent quenched equilibrium that's captured by this chemical reaction. This is roughly in the 1 to 10 bar range, about 1,000 Kelvin. That's not a habitable environment. And so then here's just a simple cartoon of what we think is going on this planet, where the planet has a thick atmosphere. And we think that that reaction between CO2 and methane, it's being quenched. So what that means is the kinetics get frozen in, because as air is moving its way up the atmosphere, eventually you reach a point where the temperature decreases enough that the reaction rates cannot keep up with that decrease in temperature, and you have a quench level. And we think that that quenched composition is then carried up into the upper atmosphere, where then the astronomers are able to derive the composition. So it's like a message from the deeper atmosphere that James Webb was able to detect. All right, I think we got to step things up because we're going to run out of time. Another question we try to address, remember I mentioned that ammonia can be removed by liquid water. And this can be more generally described as the missing ammonia problem, where you would predict that bodies that formed out of primordial gases should contain nitrogen, so where's all the ammonia? And I then introduced another geochemical trick that we can play to try to constrain this problem. So that's to imagine giant planets as big mixtures, where this is just a simple cartoon showing they form through this process known as core accretion. This is just a bunch of planetesimals and pebbles that collide in the protoplanetary disk where these planets are formed. They form large cores, and then if those cores form fast enough, they can gravitationally capture some gas, primordial gas, which is hydrogen and helium. So from a geochemist point of view, what this basically looks like is a mixing problem to me, where you have this gas here, which is the solar nebula gas or the stellar nebula gas, and then you're just mixing in solids. These solids might come from outgassing of the core, or as when accretion is continuing, you might have some of that gas present, and then planetesimals are being ablated in that primordial atmosphere. And that in effect, is a mixing problem, which is great because as geochemists, we know how to solve mixing problems. So what I did is I just defined a set of model ingredients based on things we know, like meteorites or comets. And we asked ourselves, well, what if you just mixed all these things together? What would you predict for the element abundances? And so then you can define and draw these mixing curves here. And I like to draw elements versus elements. I think that's just a geochemist thing. So on the horizontal axis, it's a carbon enrichment versus protosolar. So protosolar is 1. That means that's the primordial gas that you start with. And then you have a nitrogen enrichment, and then you have a mixing. You have these mixing curves. And the way to think about mixing, this is where my chemist background comes in. It's kind of like a rock titration, where you start with this gas, and then you're just basically adding rocks, like little bits of rock, and you start at that 1-to-1 point, and then as you move up these curves, you're adding more and more rock to that mixture, and the elements are achieving mass balance along these curves. So it's interesting if you do that, is although the astronomers were shocked that nitrogen is depleted, you would predict if rocky building blocks provide nitrogen to planets and carbon, nitrogen is intrinsically depleted in planetary building blocks for the most part. And then you can provide some of the constraints we have from the planet. So in this case, I defined 2 constraints because we're kind of uncertain exactly how much nitrogen the observations indicate. So what I indicated here is there's a conservative upper limit. This is like your worst case nightmare scenario. You could admit quite a bit of nitrogen still. And then a practical upper limit is kind of like if accounting for what's probably real on that planet. So let's focus on a practical upper limit shown here because it's kind of interesting. And you could see that if you do these mixing curves here, I confirmed that the astronomers are not crazy, and there actually is a nitrogen crisis on sub-Neptunes. You could see for these mixing curves, you'd predict somewhere up here, and if the planet is in this practical region, then there's nitrogen that has to be missing. So what we proposed to explain this is there's another way to remove nitrogen, and I'm not the first to propose this, but it's to invoke not a liquid water ocean, but actually a rock ocean, or a melted rock ocean, a magma ocean, where you have silicate melt. It turns out that the petrologists have been busy, and if you have a highly reduced system, nitrogen can actually speciate to form nitrides or ammoniated species in silicate melts, and those have high solubility. And people who make these models of pressure and temperature and structure of exoplanets, they predict for a sub-Neptune that the surface conditions can be truly astounding. The temperatures may be several thousand Kelvin and hundreds of kilobars in pressure. So these are extreme environments. Perfect for a magma ocean. And in fact, this was suggested earlier by Oliver Shortall to possibly explain K218b's missing ammonia. So in this case, I agree with his proposal for TOI 270d, and we then did further calculations based on the the oxygen budget of the atmosphere, and we concluded that it appears that reducing conditions prevail. So to put it all together, I'm going to wake you all up right there. We think this is the cartoon version of what might be happening, where there's like a combination of factors that might be explaining what JWST is seeing, where the planet is intrinsically depleted in how much nitrogen it started with by forming from like chondritic building blocks. That's number one in the sequence. But then we also think that a magma ocean might be needed to push the nitrogen budget over the edge and remove that excess ammonia into a magma ocean shown at the bottom here. And then the rest of the atmosphere appears to follow just simple equilibrium thermodynamics, where as you move up the atmosphere, the gas mixture is continuously respeciating itself to be stable, and then eventually, when you reach the quench level that we derived earlier, that's when everything gets locked up, and then that quench composition, we think, is brought to the upper atmosphere of the planet, which is called the photosphere. That's what JWST sees. So in a sense, the exoplanet problem is very similar to the Enceladus problem or other planetary science problems, right? So we see stuff up at the top. That's kind of like a plume on Enceladus. I know it's crazy to compare this huge planet to a small moon, but the essence of the problem is very similar. We see something at the top, and then we're intensely interested in all the juicy details of what's happening below. And that's where I think there's a solar system exoplanets marriage that's starting to develop. All right, maybe I just have like 5 more minutes. This is some newer work here. This is on LP 791-18C. And this is another discovery that happened when I was doing something probably unproductive during Christmas break. One of my colleagues, Xin-Ting Yu at UT San Antonio, she sent me a Nature astronomy paper that was published in December and said, hey, this is kind of cool. So I said, okay, maybe I'll read this. And LP 791-18C is another sub-Neptune that orbits in this temperate region. So here's a comparison of the 3 planets we've been talking about. And LP is very similar to K2 in many properties. Like its mass is around 7 Earth masses. It's a little bit warmer if it has a similar albedo to K2-18b. What about the spectra, though? It turns out they're not the same. So they both have methane that were detected in their transmission spectra, but K2-18b and TOI also have CO2. This planet does not, or it hasn't been detected at least. This planet has smaller absorption features, and only methane has been detected. And one of the really interesting features is has the spectrum has a sloped continuum. So the continuum is just a fancy word for the baseline of the observation. And so you can see it's sloped downward when they fit a model to the spectrum. That's shown in that brown region. And that's an indicator of small haze particles in the atmosphere that have a stronger influence at shorter wavelengths. So then I thought, well, what does this all mean? And the authors of this paper is led by this former student named, I forget his first name, but his last name is Roy. They remarked that because you lack all these oxidized species, perhaps the planet is intrinsically poor in water, because water is a great way to deliver oxygen atoms to a planet that can participate in chemistry. So I thought, well, I buy that. That makes sense. But the more fundamental question I thought is, where does all this methane come from? This seems to be an important feature of the planet, is methane. Methane can make haze. And then I thought to myself, well, what does this remind me of when we're thinking about this solar system exoplanet connection? It reminds me of Titan. And I've loved Titan for a long time. Titan has a methane-rich atmosphere. And we did some work. This is led from a former postdoc of mine, Kelly Miller. We have lots of data from Titan, lots of isotopic data and noble gases. So we can do some good work on Titan. And this just shows a plot of the argon-36 abundance. This is like a tracer of the building blocks of Titan. And then the nitrogen isotope ratio. And what she discovered is that Titan's atmosphere falls along a mixing curve for its N2. You can see that if you draw a mixing curve between organics, So this is like primordial carbonaceous stuff. We call carbonaceous chondrites carbonaceous because they have a lot of organic matter. It's like you can think of it as tar or soot. And if you have that tar and soot and you mix it with ammonia, you can define this mixing line and you can reproduce the Titan data. So we concluded that organics, these are not biological organics, these are organic building blocks of planetary bodies. They are important in the solar system. And these are shown some other calculations I did. These are for Pluto. Pluto has a lot of methane and N2 on its surface as well. And it turns out that if you cook organics inside a body like Titan or Pluto, you make a lot of methane. So I thought, well, what would happen on a big exoplanet? First, you might be wondering, how do these exoplanets get organics? And this is actually, I learned this is a hot topic in astronomy. Astronomers like to define these lines in the protoplanetary disk where planets form. I showed you in slide 2, the snow line. That separates where water is gas and water is ice. A new concept that has emerged is known as the soot line. And that's where organics can be stable as solid matter. And if you go interior to the soot line, the temperatures get high enough where organics get broken down into smaller pieces. So planets that form outside of the soot line, that's a sweet spot where they can acquire a lot of organic matter that's mixed in with all the rocks that they form from. And if you're in between the soot line and the ice line, that's prime territory to form planets with lots of carbon and not much oxygen, because you get all the carbon from organics, but you don't get the oxygen from water ice. So we thought, well, let's do some calculations here. What if you imagined that this planet accreted lots of rock mixed with organics, kind of like a carbonaceous chondrite, and this shows a formula of organic matter that's been studied inside carbonaceous chondrites. It looks like this. If you ever heard of the OSIRIS-REx mission to asteroid Bennu, this is an image that was taken. It looks like charcoal, from your barbecue grill, for example. That's what the stuff looks like. And if you do a calculation where you just imagine mixing this with H2 and helium gas in a big planet and equilibrating it, this shows an example of what happens. Again, it's like a titration. In this case, you have a hydrogen atmosphere. And imagine titrating. You're like dumping bricks of charcoal into that planetary atmosphere. What do you think happens? Well, if you have a lot of carbon and you have hydrogen, you make methane if you cook it high enough. And that's what these calculations shown here. As you can see, as you add organics to the mixture, the methane abundance really shoots up. So we thought that was interesting. And what's interesting about organic matter is it's intrinsically depleted in oxygen atoms. That it seems to fit, the pieces seem to fit with the observations where you have abundant methane and then oxygen seems to be missing on this planet. So what we think happened is this diagram shown here. And keep in mind, we don't know what this planet actually looks like. I've just stolen Titan's appearance for the exoplanet. But we've detected evidence of haze particles high up in its atmosphere, and we know that it contains methane in the atmosphere. So here's the evolutionary scenario where we think that the planet could have formed from organic-rich building blocks that were either delivered in that primordial core or that subsequently were accreted into its atmosphere. And if you mix those organics with the hydrogen gas, you have this process happen, which is known as hydropyrolysis. This is actually studied by chemists because they're interested in turning coal into gas. And if you do that cooking process, you can make the methane. And once you have the methane, then you can start a carbon cycle. This is not a habitable carbon cycle, though. This is an uninhabitable carbon cycle, but it's still really cool chemistry where methane can serve as a feedstock through photochemistry. You make the haze that we see, but then the atmosphere is very deep, very hot and thick, so when those haze particles eventually settle into the deeper atmosphere, you have another generation of this hydropyrolysis, so cooking organics again, and then you complete the loop and you regenerate methane, and then that process might just go on forever on this exoplanet. So we think this could be an example of not a habitable world, but an exotic type of world that we've learned something about by working with the JWST data. And with that, I'll take you to my last slide and answer any questions.
Thank you so much, Chris. Questions? I will bring the microphone over.
How does the soot line relate to the habitable zone? Like, is there a relation, or does it depend on, like, the protoplanetary disk size, or what?
That's a great question. So a lot of people are mystified by why Earth doesn't have as much carbon as it does. And we think, well, I shouldn't say we're still working on it, but some astronomers and geochemists think that Earth formed interior to the soot line. So all that primordial organic matter. So if you look at like interstellar molecular clouds, there's a lot of abiotic organic matter that just formed from ice chemistry when you irradiate a bunch of ices. And when you first form a solar system, a lot of that material might be inherited into the primordial disk. So if you're going to form planets that lack carbon, like the Earth, although we're carbon is not abundant on the Earth. A lot of that soot needs to be burned off to be left with rocks. And so we think that Earth formed interior to this soot line, so we mostly lack abundant carbon. Otherwise, the Earth's surface environment may have been much different. We could be more like LP 791-18C, which would not be good for us.
Yeah, thanks so much, Chris. That was fascinating. I think my question for you is maybe something that I've been struggling with. So we have these like pretty plausible stories, I guess, for the nature of some of these planets that, you know, the CO2 is produced thermochemically and mixed up, and we can maybe explain the lack of ammonia through forming with a bit less and it dissolving into a magma ocean. Like, that seems pretty plausible. But how do we go further than that and actually confirm these pictures? Because I feel like there's diminishing returns on JWST observations. Your abundance constraints don't actually get that much better if you hammer it with more transits. Like, do we need better petrology, like solubility of nitrogen under these extreme conditions? What do you think are the gaps that are going to really like confirm these pictures?
Well, I think there's many things we can do. One thing is we can get geoscientists interested in this problem because they know how to approach these problems. So for like solubilities of volatiles in melts, this is something that geochemists and petrologists know how to do. So to involve them in this work, I think, is going to naturally lead to insights. And then another thing with observations is I think we got to then take things the next step where, so in geochemistry, often what people did is they're studying geothermal gases just based on speciation. The next step from that was isotopes. So I think we need to start thinking about, can we acquire isotopic data from exoplanets? And that may be possible, not with James Webb, but some of the extremely large telescopes that are going to be starting up in 5 years or so. Those might have some promise.
Thanks.
Thanks. The idea of isotopes by very large telescope is exciting. I want to ask you about the question of planetary evolution. What you've shown us here are these, exquisite snapshots of moments in time. But of course, you wouldn't have, in our own planet's history, you wouldn't know that the composition of the atmosphere has changed. So how do you think about situating your observations relative to the life cycle of a solar system and of a planet? And do you think that is there something to be learned? Like, are there categories of life history of planets that might come out of this? Or do you think it's mostly random and each planet is its sort of own special life to be lived?
That's a lot of great questions. So I have a whole nother lecture about planetary psychology where I think about nature versus nurture on planets, really. Because you can almost draw an analogy with like people and how there's similarities, but they're also different in the details. And I think that's going to be the same is going to be true with planets, is we'll probably be able to define buckets where there's categories of planets, but in the details will be the devil, right? So that'll be interesting. The astronomers have actually they do a huge favor in helping us to understand the temporal dimension of planets, because we're never going to get, never is a bad word, I shouldn't say never, it'll be very difficult to get the kind of information to address the time dimension for these types of planets I described. What's great about astronomy is there's so many planets out there that we can get, although we can get a snapshot of each one, we can look at a lot of planets, right? And so we can get all these snapshots throughout their evolution, and I think the hope is that we'll be able to piece things together. And that's been done a lot in astronomy, where we learn about the evolution of, let's say, protoplanetary disk, because we directly observe those disks. We can see these disks have gaps in them. Those have been imaged by, for example, ALMA. And you can see that newborn planets are forming, and that informs these ideas that people develop. So I think that's the key, is we have people like me who are working on these snapshots or case studies of individual targets, but then we also have other folks who are doing population surveys, and you're looking at hundreds of planets, and you're trying to look for big scale features that separate their evolution.
If I may, I want to follow up on the question kind of bias. You mentioned that first planet, whose number I can't remember, has a long Earth. It's got a long day, long year. Surely that's a bias, because if a planet only orbits its star every 200 years or whatever, the chances that you see a transit are correspondingly small. So do you have comments about the bias in what we're finding out there?
Oh, yes, I have some thoughts. I run the risk of saying the wrong thing, because this is not totally my area of detecting longer period planets. But you're right, there is a bias with the transit method. Eventually, we're hoping to do direct imaging of some of these planets. That's where you look at the reflected starlight off the planet's surface or atmosphere. So that's one thing. I know that there's some new facilities being developed. So there's a big new telescope called the Roman telescope that's going to launch, I think, next year. So it's coming right up. And then there are these other observations where people are able to detect planets using gravitational lensing. And at the risk of venturing far outside my expertise, I think they are finding that super-Earths are fairly common further out.
Thanks. Other questions?
Do you think the sub-Neptunes can have iron or sulfide cores?
Possibly. This is actually a controversial issue. So people who do thermodynamics, those conditions of pressure and temperature are very extreme. So the question is whether or not metallic iron and nickel is miscible with molten silicates. And there's actually a large region of parameter space where they would be miscible. So you may not actually have an iron core for many of these sub-Neptunes. I don't know how you detect that. Maybe somebody could be clever about detecting magnetic fields, and there might be interesting signatures. Yes, of course.
Hi, I want to preface by saying that I'm not very well versed in ocean dynamics, but I was wondering a bit for those Haitian worlds. I know we'd be missing a lot of those key constraints, like the rotational rate of those planets. I was wondering, based on what we expect from those models, what do these models say a bit about the ocean dynamics on those worlds, and what that means about the chemical mixing in that ocean layer?
Oh, I don't know the answer to that question. It's a good question. Those planets orbit close enough to their host stars that they're believed to be tidally locked. So kind of like the Earth's moon, we always see the same face of the moon towards us. Those planets will be irradiated on the day side, and the night side is always the night side. So there might be some interesting aspects of how that affects ocean circulation. But I don't know any. I'm sure people have started to think about that, but I don't know the details.
So, in this lecture and the last one, you emphasized the triad of signatures of habitability, temperature, chemistry. I think pressure was the other one.
Liquid water, energy, and elements.
Okay, thank you. I'm wondering how surface level gravity fits in there, particularly since in a lot of speculative astronomy, these super Earths or sub-Neptunes have been assumed to be high gravity worlds.
It depends on the planet. So if you have, let's say, a planet with a really thick atmosphere, like what I showed for TOI, if you have high gravity, that means the pressure is going to quickly increase when you go deeper because it's just rho GH, right? So G is directly affecting pressure. So that what that ends up doing is that favors methane, because methane is always favored at higher pressures. So that'll shift the balance towards methane, for example. And that's why like brown dwarfs have a lot of, so that's like, between Jupiter and a star is a brown dwarf. It's a planetary object. And so those are massive objects with much greater gravity than Jupiter, and they have a lot of methane because you're quickly reaching higher pressures before the temperature gets too hot, and then methane is stable. For a water world, you'll have a similar effect. Maybe Baptiste would know the answer to this question, is how a quick increase in pressure would affect chemistry, or maybe that's like the whole basis of a research program.
To what extent are some of these experiments possible on Earth? Would they only be able to be simulated in computer programs as we slowly advance those fields? Or is there a possibility we could create technology to actually physically simulate some of those environments?
Ooh, I better be careful. There could be an igneous petrologist in the audience. So I think at hundreds of kilobars of pressure and 5,000 Kelvin, I think you're going to be hard pressed to do a large-scale macro-level experiment of studying the nature of those kinds of materials. People do use diamond anvil cells and those kinds of approaches. So although those seem like insane pressures, for example, those pressures actually occur in the Earth's mantle, and people have developed approaches for studying deep Earth conditions. So it's just finding clever ways, or actually just finding ways to communicate is really a critical barrier where the astronomers and folks who are planetary scientists can talk to geologists and geophysicists, volcanologists, and so forth to get their insights, because we don't need to keep reinventing the wheel. There's people who know how to do this stuff, and they do this stuff really well. They just may not know what the nature of the problems we face on exoplanets.
So sort of similar to that, is there more research to be done on, say, the actual planet Neptune that could potentially tell us more about sub-Neptunian planets in different solar systems?
Yes. So it's important because our solar system is kind of like the ground truth. And some of the measurements that we can make in the solar system, we just can't make on an exoplanet. So I'll give you one example. I really love noble gases because they are extremely useful indicators of the formation of planetary bodies and how they acquired volatiles and what happened to the volatiles. It's very difficult to measure noble gases on an exoplanet because they don't produce key spectroscopic signatures that are easy to detect. But what you can do is you can design entry probes to go into Uranus or Neptune, and you can make those measurements. Or you can make a probe that goes into the atmosphere of Venus, like the Da Vinci probe will do, and you can make those measurements. And then that's where the marriage between these two fields becomes so powerful, is by using this ground truth to help inform our modeling, and then we can try to extrapolate these models very carefully to exoplanets.
Thank you. Let's take one more. There is another one. Right.
I should mention, so in the background of the slides, on the left-hand side, that is a planet around a pulsar, which is the remnant of a star that went supernova. These planets were initially thought to be impossible, and they actually exist. And the right-hand side here, this is just an artist's depiction of what a newborn planet might look like, where it have this glow because it's still cooling from its accretion. So these are just two more examples of strange places.
So, question about the sort of very interdisciplinary nature of sort of going throughout your lecture yesterday about Enceladus and sort of your more local planetary science, and then with your talk just now about exoplanets. Still formatting in my mind exactly the question, but in the sense of you with a geochemical background, ESS, and chemistry, what would your advice be in sort of the context of having an interdisciplinary approach and all these different fields? You talked a lot about astronomy, some organic chemistry, geochemistry. What would your recommendations be to undergrads or soon-to-be graduates who are trying to get into these kind of fields and these very interdisciplinary fields such as exoplanetary science?
Yeah, so my recommendation would be to get a really strong background in physical sciences, because having a broad, strong background allows you to apply quantitative methods to problems like this. And if you have that background, then you have a big toolkit that you can deploy. So in these approaches here, they're actually kind of different, right? So it's not like I have one set prescription that I apply to every planet. It's sort of like you get new data, and then you got to figure out what to do. And if you have a toolkit that's broad enough and deep enough, then you have all these tools available, and you can figure out, well, hammers are good for this one, but a screwdriver is good for this one, and so forth. But it's really important. I mean, I'm not going to try to discourage anyone from exploring really cool questions, but you need to have a strong background in one of the core sciences. It can be geology, it could be physics, or it could be chemistry, for example.
Thank you.
Yep.
All right, I want to add something to that, which is make friends, because none of this stuff happens with individuals because it is so interdisciplinary. Yep. So please join me in thanking Chris Glein for his visit.
Thanks, everyone.
And I will let you guys go, but if you want to stick around for his answer to my final question, you may. Talk about DMS, please.
Oh, DMS. DMS is the molecule that shall not be named.
Is that all you're going to say?
Well, DMS is thought to potentially be a biosignature, but the problem with finding DMS on an exoplanet is it's a non-unique solution to an inherently noisy spectrum.
So it might not be real.
It may not be real, or if it's real, it could be some other molecule.
But if it's not some other molecule, it's life, right? That's, as far as we know, that's...
I don't know if we could say it's life. It's kind of like the Venus phosphine problem,
okay.
where we say there's a molecule we don't understand, therefore it should be life.